It's my pleasure to introduce Arthur-Cesar and Bhatt, who will tell us about stacks and p-adic Hodge theory.
Thanks a lot for the introduction and for the invitation to speak. Right, so I want to speak about stacks in p-adic Hodge theory of rigid spaces, and I guess there are various ways of motivating this. The study of such geometric objects. I want to start with a specific one. So let X be an adic space over QP prime P. For example, X is a rigid space. We can consider the V side of X. So a certain category with a quadratic topology, let me recall. So it's a category of perfect weight spaces over X. Endowed with a V topology, which is topology which is generated by surjective maps between affine perfect weight spaces. And this side comes with a structure sheaf, which I will just denote by O, which simply sends a perfect weight space T to global sections of the structure sheaf. And the question I'd like to address is whether one can understand or describe the category of vector bundles on this side, which I will denote like bun XVO. So all modules which are locally defined projective, or more generally, if we want to do something at the derived level, maybe we want to understand the category of perfect complex on this side, in terms of say the analytic topology on the rigid space, on the adic spaces. All right, so this V topology is a very fine topology. So a priori, we are considering objects which become trivial locally only in this topology on like maybe very large covers. And we'd like to see if we can understand this category in terms of like maybe more familiar topologies. And first thing I should say is that if X is perfectory, then in fact, this category of perfect complexes is just the same as the category of perfect complexes for the metal topology, or equivalently for the analytic topology. So for vector bundles, this is due to Keldaya U, and was extended by Anschutz and myself, building on. So this is basically just telling you that you have descent for the topology for perfect complexes on perfect weight space. And we will see many more, I mean, much stronger analogous descent results in the next talk. So that's about the perfect weight case, but in general, this category is much bigger than the analogous category for the Etan topology. And it's already visible in the simplest possible example. So if you take X to be QP, or I mean more generally, far of any finite extension K of QP, then you know that, let me just write the statement at the level of vector bundles. If you look at vector bundles for the V topology on X, well, QP has a V cover, which is given by space CP, which is a perfect weight space. And on a perfect weight space, on the perfect weight space space CP, shown by the previous result, the perfect complex, a vector bundle for the V topology is just the same as a finite dimensional CP vector space. And then you have a descent too. So this category is just the same. The category of semi-linear, continuous, Galois representation on finite dimensional CP vector space. On the other hand, if you look at vector bundle for the eta or analytic topology on X, it's really just a category of finite dimensional QP vector space. And here the functor is really simply, if you have a finite dimensional QP vector space, you can just answer it by CP and look at the action induced by the Galois action at CP. So that's very far from being an equivalence. For example, all positive or negative taste twists are not visible.
Sorry, could you please remind me what's your definition of perfect complex? I mean, I guess that you don't assume that X is QCQS, so I mean.
I just mean some complex of O modules which locally for the V topology is isomorphic, quasi-isomorphic to bounded complex of vector bundles.
Okay.
Okay, and of course, this is a very classical example which has been studied by in work of Sen. And I don't want, for time reasons, to recall all the statements, but let me just say that what Sen in particular did, he showed that the functor, let's say, described rather quite explicitly a full subcategory of this category, which I will just have QP and namely prove that the functor which sends the pair m comma theta, where m is the finite dimensional QP vector space, and theta is some endomorphism of m, with the property that there is some condition on theta. You want to assume that if you look at exponential of the power series defined by the exponential of theta times logarithm of the cyclotomic character applied to sigma, this converges for any element sigma in the Galois P. To any such, you can attach the tensor product of M, is CP over QP, and this is under the action of Galois. And that this defines a fully faithful functor. Right, so you don't really describe all the category, but at least you describe a bigger subcategory than just the category of dimensional QP vector spaces, which would be the case where the Higgs field is zero. Sorry, the same endomorphism. And this has been generalized quite a lot since work of Faltings almost 20 years ago. So if you care about more geometric situations, it's maybe not so obvious from this picture, but the right thing you would like to consider is, so you have to think to this as like a vector bundle for the analytic topology, and then you want to put some extra data. And the extra datum you want to put is a Higgs field. Or if you have a rigid space over a p-adic field, maybe you want to consider a Higgs field together with some Sen endomorphism with some compatibility between them. And you've seen many examples of such statements in Anetol's work. My first goal is somehow to explain how to revisit some of these statements using the prismatic stacks that has been defined by in work of Bhatt-Lurie and Drinfeld. So let me recall briefly the setup. So I write frac X for p-adic formal scheme. So what Bhatt-Lurie and Drinfeld do is they attach functorially in X they construct stacks, which any of them, but the only one I will care about today are the prismatization of X, which contains a certain closed substack called the Hodge stack. And the idea is that these stacks geometrize prismatic, respectively Hodge state cohomology. And let me briefly recall that you can think to that construction in two ways.
So the formal scheme is it's not smoothness.
Here it's not necessarily smooth, but I will very soon specialize to the smooth state. So either you somehow define the stack by descent, then you have to prove the necessary descent results, but basically reduced to the case of semi-perfected rings. R, and in this case, the stacks are just given by formal spectrum of prismatic cohomology of R. Or the formal spectrum of the reduced prismatic cohomology. So this perspective someone makes clear that what you are constructing is a stack, are stacks with the properties of cohomology of the structure sheaf, and then recovers either prismatic cohomology or reduced prismatic cohomology. But you can also give a direct construction without assuming knowledge of prismatic cohomology. And I don't want to fully recall it, but alternatively, you can first define stacks ZP prism and ZP Hodge state as a certain moduli stacks of Cartier bit divisors. And then, whenever you have a thin nilpotent algebra R, together with a map from spec R, any of these stacks, so let me maybe choose the first case. So the datum of this map is the same as the datum of certain generalized Cartier divisors in the bit vector of R by definition of ZP prism. And then you can consider and define X prism, the R points of X prism to be X of spec of WR, where I is the Cartier divisor, as I say, the generalized Cartier divisor corresponding to the datum of this map. And the definition in the other case is exactly similar. So this is understood as a one truncated animated ring. So it has both a pi naught and a pi 1. And this is, I think, in a Vargas style definition by transmutation. The idea is you first define what the stack has to be for your base from a spectrum of ZP over which everything lives, and then you just need to define what the prismatic what the prismatization of the affine line should be as a ring stack. Okay. Okay, so for this motivating question I have, I won't use much of prismatization, and maybe I will come back to it later. For now, I will focus on the Hodge state stack. So let me say a little bit more about the structure of the Hodge state stack. So it comes equipped with natural map pi of X Hodge state to X, which has the following properties. So first of all, pi is an isomorphism. If X is perfectoid. Integral perfectoid. And second property is that you can understand it rather explicitly in the smooth case. So if X is smooth over the ring of integers of the p-adic field, so K is complete discretely valued field with perfect residual field, or smooth, let's say over OC, where C is complete algebraically closed extension of QP. I could actually replace here OC by any integral perfectoid ring, but for simplicity, we just consider the following two situations. Then this is a gerb, like pi realizes X of J as a gerb over X with like which is bounded by an explicit formal groups. So I can give quickly like two basic examples. So most basic example is the case where X is formal spectrum of CP. And then the bound of the gerb is given by, in this case, this gerb is split. It's just it's a specifying stack. And the automorphism group is GM sharp. It is the divided power envelope of the unit section. So it's formal spectrum of direct sum over I ZP T minus 1. So you add all divided powers. So, of T minus 1. And another explicit case is, let me look at the case where X is, say, smooth over OC, so that's the geometric case. Then the bound, then is the gerb is not necessarily split, but the bound is given by something very analogous to this. So you consider the tangent bundle of X over OC, and you take the divided power completion of the zero section. And I forgot that there is a Boykian twist, but you can also ignore it in the geometry. Okay. So what are the consequences of this result for us? Well, the consequence of statement 1 is that you can construct a pullback functor, which I will call alpha upper star, from perfect complexes on the Hodge stack to okay, so now let me be careful about my X. So X is my p-adic formal scheme, and I will let X straight X be its generic fiber. Analytic space over QP. So I do get a natural functor like this, simply because whenever I have some affinoid perfectoid spar R plus mapping to X, then I get a map from the Hodge stack of formal spectrum of R plus to the Hodge stack of X by naturality. But as I said, by point 1, in the perfectoid case, the map is just an isomorphism. In other words, the map from formal spectrum of R plus to frag X will naturally lift to the Hodge stack, and you can just pull back your perfect complex along this map. And because here P is inverted, this will actually factor through the isogenic category. So you get such a pullback functor. And so And the advantage of point 2 is that it gives you, in good cases, an explicit description of the source category, so the isogenic category of a complex interrupted stack in terms of étal data on X. So again, let me just give 2 examples, the 2 examples I gave before. So when my formal scheme is just cozy P, then this case has been analyzed by Bhatt-Lurie. And what you get is just the category of perfect complexes for the ring QP in a ring order theta, such that the cohomology groups of this complex are finite dimensional over QP. And you have some condition on this homomorphism that theta p minus theta act topologically nilpotently on cohomology. So this statement just basically follows from what I said here. You have a classifying stack for GM sharp, so you can, for example, analyze perfect complexes on this via Cartesian. So let me also quickly say something about this case. So if X is smooth over OC, and you assume that X Hodge tail over X is split there. So this would be, for example, locally always the case. For example, if X is affine. Then you get that this isogenic category is the category of, let me say, X perfect complexes with topologically nilpotent X. Again, this topologically nilpotence condition can be seen from, for example, from the perspective of Cartier duality by using the fact that Cartier dual of GA sharp is a formal completion. So the classifying stack of GA sharp is a formal completion of GA. All right. So now, to make this interesting, you need to know something about this putback functor. So that was the main result we proved in joint work with Johannes and Schutz, Ben Hoyer. So we put ourselves in the same setting, so let X be smooth, so a p-adic formal scheme. This generic fiber multiplied straight X. And assume that either X is smooth over OK or smooth over OC, or more generally any integral perfect category. And then we prove that the functor is full phase. So as a consequence of this, you see that in good cases, you get a fully faithful embedding. Of a certain category of Higgs. Higgs perfect complexity. In the category of perfect complexes on the B side of the Higgs. Okay, so why do I say in good cases? Well, so to interpret this fully faithfulness statement in terms of Higgs bundles, you need to know, I mean, it's not always true, as I've said, that this gerb splits. Only in the, a priori, only in the split case, you can really interpret perfect complexes on this stack in terms of Higgs bundle or Higgs perfect complexes. So in the arithmetic case where your rigid space live over K, that's not an issue. But in the geometric case, you need to put some assumption. So these are a local assumption, like assuming that everything is affine. Or you can also do better. For example, you can assume that your formal scheme leads to A inf modulo psi square. This does not really ensure that the stack splits, but that's still good enough to give you, up to shrinking the category of Higgs perfect complexes you consider, some fully faithful. So this must really be thought as a generalization, if you want, of this result of Sen that I explained at the beginning.
Sorry, so in the smooth over OK case, also there's some shrinking happening on the depending on the ramification effect of K over QP.
I don't think so in this case, because the Higgs field is automatically input.
No, to split the gerb, sorry.
To split the gerb. Wait, so am I saying? I don't think you really need, I mean, so in this case, sorry, also my formulation is a bit lazy. So what you really get in the arithmetic case is not just a Higgs, or like a Higgs set number. But after pullback to C, if you are already defined over OK, you automatically have the lift to, I mean, in this case, actually, the fact that you're already defined over OK will actually force the Higgs field to be nilpotent. So I don't think.
You don't have to worry about splitting the gerb, just the geometric part of the gerb.
Right, I don't think so. But I may, okay, maybe I'm just missing number, no, but I think in the arithmetic case you have no assumption.
Sorry, what do you mean by Higgs complex? I can't read this.
Right, I mean the Higgs, I mean.
The thing with the theta? Is it
yeah, I mean the perfect complexity tangent bundle, which when you push forward to X is already.
So I think it's the right fake idea, or I'm just because it looks different to the other one. Above something.
It looks different from the other ones.
In the case of the
I'm not claiming that you get all perfect, all like Higgs perfect complexity. There is always a condition on the Higgs field, which is similar to the one we saw in this result. Or already what happened in the case of chain theory. There is always this smallness condition that you need to ensure that the Higgs field or the same endomorphism is close enough to topologically nilpotent enough.
Are there any cases where upper star is not fully faithful?
Again?
Are there any cases where it's not fully faithful?
Well, I think in the semi-perfectoid, like not perfectoid case, you can see that it cannot be fully faithful. Because prism alpha and the perfectoidization will be different. So you can't really. Yeah, I don't want to say to discuss the proof of this statement. So yeah, you can't really prove it by descent. You really have to. I think you really have to use the smoothness assumption or general statement. Yeah, regarding the proof, let me just say that some of the construction nice feature of this formulation is that the construction is functorial in X, so you can, once you have defined this functor, you can really just argue locally on X, so you can reduce, I mean, you have something smooth, so it's locally étal over the formal torus. You can even reduce to the case of the formal torus, and then you have to use the explicit structure of the germ to, in the end, reduce to some kind of Galois cohomology computation, which happens in any paper on p-adic Simpson. But somehow, I mean, it's always somehow reduced to such a computation in some sense, at least for the fully faithfulness part. Here somehow it just naturally, so it's kind of Galois cohomology of a certain third ring, which here you don't have to guess a priori, just forced on you by the geometry of the stack. I mean, this third ring is basically the ring of functions in this formal group scheme, which appears as the bound of the germ. All right. Okay, so that's was a. Yeah, I think one big issue in the study of the p-adic Simpson correspondence is that you can often do like local constructions, and then one big difficulty is always how to glue them. It's not so clear which choices you are making and how it depends on them. And I think in this formulation, I mean, it at least kind of separates what is like really functorial and natural, and what somehow requires some choices. I mean, at least here what requires some choices is how you, for example, want to split the germ to really connect the source category to Higgs bundles. But okay, still this statement has two main drawbacks. Quite obvious. So, first of all, well, you need to assume. I started with say a smooth rigid space, but I need to consider these stacks and understand them. So I need to actually assume that it has a smooth formal model. Asking that X has good reduction. And another obvious problem is that it only describes the subcategory. Also, category of perfect complexes for the V2. This functor is very far from. It's far from being essentially solved. So this leads to the second part of my talk, and the main question is to try to adapt this strategy to a more general context. Is it possible? Can one define the Hodge state stack, or more generally the prismatization? Directly for the rigid space itself, or any rigid space over QP, without passing through formal models. So that's what I want to try to explain the construction doing this, which is very much in progress. And joint discussions with Sanchez, Juan Esteban Rodriguez Camargo with me, and Peter Schultz. Okay, before trying to sketch the construction, I want to make two, we'll start with two observations. Or to try to motivate what we will do next. So the first observation I want to make is that, so as we've seen in, for example, this first way of presenting Bhatt-Lurie's construction, prismatization of a formal scheme is a geometrization of prismatic group. So if we want to define some prismatization for rigid spaces or more general adic spaces over QP, we need somehow to maybe make a guess for what prismatic cohomology of a rigid space can be. So let's try to see what is reasonable in maybe a specific situation. So let me put myself in the relative setting. So assume that you have this formal scheme. We are in the geometric case, the formal scheme over OC. Where C is, as before, a complete algebraically closed extension of Q. So then we know by the results of Bhatt-Lurie and Bhatt-Lurie that prismatic cohomology of X. So let K is a ZU field of C. But if I base change prismatic cohomology lives over A inf. If I base change to WK, I recover crystalline cohomology of the specified. Let me assume. So that's something which visibly depends on a special fiber of X. But what you can observe next is that actually, if you restrict if you only look at, if you remove this crystalline point, so if you restrict to star inf, which you have removed, so locus where Teichmüller of pi is 0, where pi is a pseudo-uniformizer of C, which is something I want to denote y0 infinity for content situation. Then this actually only depends on the generic fiber. Okay, so it's basically because this restriction is something that can be described by a result of Farc, say, as a, let's say, modification of two vector bundles on the Farc content curve, and each of these vector bundles can be described purely in terms of the generic fiber. So first naive guess could be to, if X is no, say, a smooth rigid space, you may hope that whatever prismatic cohomology of X is, you may want this object to be quasi-coherent sheaf on Y0. I did not put any properness assumption on X here, so it's a priori just a solid quasi-coherent sheaf on this adic space. But this cannot work, and the reason for this is quite simple. So, I mean, naively, you could imagine that you have like formal schemes for OC. You have the functor, which is a formal scheme. You have the generic fiber functor to rigid spaces over C. And here you have prismatic cohomology, which gives you complex of 8-inch modules. And now we just like localize away from this crystalline point. And you could hope to get such a functor. But this does not happen, as I just said, because, for example, if you take X to be the formal spectrum of OC P, yeah, before. Okay, so in this case, the generic fiber is empty. X. But prismatic cohomology of this is given by the ring decrease. And it is not true that you consider prismatic ring decrease and you raise change over A inf to the ring of functions on y0 infinity. This is far from being zero. Right, so the picture is you have something like this. So this is the divisor of p equals 0. This is the divisor of p plus equals 0. So A pris is something which lives somehow here, on this part of the picture. And the y0 infinity is what you get by just removing this vertical axis. So I mean, even if you take some kind of completed or solid tensor product, this is still non-zero. But fortunately, things get much better after passing to the co-limit perfection. That's not too surprising, maybe, because we know that as a result of Bhatt also about perfect prismatic cohomology that it can now be described in terms of the generic fiber. Here, yeah.
If you restrict to flat, so it's OC, it's still not going to give you.
Say again?
If you restrict the subconcept flat, things which have no like a flat over OC. Your diagram.
Yeah, and that's maybe I'm not sure. On the spot, I don't. I mean, but I would be a bit surprised, but
You don't have an example of that
I
structure.
don't have an example of it.
So that's a purely p-project.
Okay, so right, so but here something you can observe is that, I mean, here we remove the locus where p flat, sorry, Teichmüller p flat is 0 analytically. So in fact, it's you can pass to the co-limit perfection, but it's not necessarily to take completion. So for example, in this example we had, that's a computation one can do. One takes the completed tensor product. This will actually vanish because somehow the Frobenius is moving everything in this direction, and so after applying Frobenius 1, you get something which lives here, and then you move more and more to the left of the picture, and this makes completed tensor product vanish. Okay, that's some kind of very heuristic justification, which I mean I won't really use, but just to motivate why what we may want to consider for rigid spaces is not literally say prismatic cohomology of a formal model, but rather some perfection of prismatic cohomology. But perfection in maybe the weak sense that you just directly take the co-limit under Frobenius and don't try to further take some completion on purpose. This last observation brings me to the second observation I wanted to make, which is going back to the first question of the talk, on the case of sense theory. Because in this case, there is a perspective on formulation of sense theory due to Colmes, which is in the style of Fontaine. So you introduce a certain paired ring and try to define invariance by tensoring with these paired rings and taking invariance. What Colmes does is that he considers a certain ring, which he calls B-sen, which is the ring of, I will write it this way, the ring of power series over Cp with the variable u with non-zero but arbitrarily small radius of convergence. So you can write it as a union of subring B sen n, where B sen n will denote the subalgebra of, so you look at power series which are convergent of radius, I think, p minus n, at least for p. And you don't have really a Galois action on each of them individually, but you have an action of Galois group of the n cyclotomic extension of QP on B sen n. The action is given by sigma of u is u plus log of or sigma in this Galois. So the idea is you have power series which are convergent with a certain radius, and you translate the variable. If you take any element of the Galois group, it's maybe not necessarily convergent with the same radius anymore, but if you take the Galois group which is small enough, it will be. And Kolmez proves that. So you can, as I said, you can do Sen theory using this ring. So for example, if D is a representation, imaginary representation of the Galois group of QP, then you can look over the Sen of B, which is some of the functor going in the other direction, as the union over all n of B times B Sen n invariance by the Galois group of QP. So what is that one? I mean, I not really recall Sen theory, but this would be a module of a prime dimensional QP infinity vector space. QP infinity just denotes the extension of QP you obtain by adding all piece roots of unity without taking completion. And it has a certain Higgs field, which is induced by the Higgs field given here by differentiation with respect to up to psi. And the reason I'm saying this here now is that if you come back to the first part of the talk, when you try to explicitly analyze, for example, what this functor is doing, as I try to sketch, you end up somehow playing with the ring of functions on the bound of the Jeb and tensouring your module with it and taking some invariance. But here, one can observe that the ring of functions on GM sharp, base change to CP, it actually embeds in B sen. And the map, you have a coordinate T in here. I mean, also something I did not say explicitly, but in this basic case, the way you see the Sen operator is given by T times Z over T. And this is explained by the fact that here T has to be sent to exponential of U, which makes this morphism equivariant for the natural action of C on both sides. And so geometrically, like this is a ring of functions on some kind of overconvergent disk of radius 0. And this is, roughly speaking, a ring of functions on some affinity disk of radius, the radius of convergence of the p-adic exponential. So p minus 1 over p minus 1. And so guided by what happens in playing with the Hodge state stack in this arithmetic situation, we may want in general to, in the particular case of spark QP, like maybe to replace this OGM sharp by something like B sen. And this is very vague, saying no. in fact, this ring Bsen has a nice interpretations in terms of locally analytic functions. So it's very closely related to the ring of locally analytic functions on the Galois group gamma of the cyclotomic extension. And so some kind of heuristic guess you can make for what the Hodge stack of looks like. So remember that for ZP itself, for the prismatic, the Hodge stack of Bhatt-Lurie, it was just given by the classifying stack of GM sharp. So here you may expect maybe the QP Hodge state will be given by something like the co-equalizer. That's just some wild guess of spar of locally analytic functions on, let me call this Galois group gamma. So I will QP going to spar of thing. But if you look at this formula, it does not make any sense because, first of all, because I put K, but QP infinity, as I said, in the uncompleted cyclotomic extensions. I mean, that does make sense, but the adic spectrum, if you take adic spectrum in the sense of Huber, this does not distinguish between this, this field and its p-adic completion. So then you would just be looking at spar of adic spectrum of the cyclotomic extension. And similarly, this ring of local analytic functions is the space of compact type. It's dense in the ring of continuous function on this profile group gamma. So if you really look at this formula in the world of adic spaces, which only see topological rings up to completion, you are really just somewhat describing the diamond of QP. So you are, I mean, in the end, the only thing you get is somehow a tautological description of perfect complexes on this space, or the B topology. So this, together with the fact that in the first observation, we remarked that passing to the uncompleted colimit perfection is enough, somehow explains why the stacks we want to construct, if we want them to be interesting, will be analytic stacks. It's because we want to be able to attach geometric objects to topological rings, and we want to do it in a way that we are still able to distinguish between, say, for example, the completed cyclotomic extension of QP or its p-adic completion. Or same for locally analytic functions and continuous functions. Okay, and so we can now come to the actual construction. Right, so the idea, again, let me, since I only have a bit more than 5 minutes left, let me just say orally that we want, in the category of diamonds, the test objects are perfect weight spaces. So here we care about perfect prismatic cohomology, by point 1. So, but we still want to see like decompleted stuff. So we need somehow to enlarge a little bit our test category of perfect weight spaces to still be able to distinguish, as I just said, between, for example, locally analytic or continuous function. So the way, so on the test category, for our, defining our stack, it says contain perfect weight rings, like for diamonds, but also things like this ring B, so ring of convergent, over-convergent power series. And so the test objects we consider are what we call, I guess, temporary name, but we call them Dagger perfected spaces. It's a Dagger perfected rings. So perfected rings, usual perfected rings, let's say perfectly tight rings. They form a subcategory of the category of your perfectly affinite ring. Of the category of tight perfects. Which are Huber rings with the topological nilpotent units. So before defining the analog of this generalization of perfected rings, you first have to enlarge this category. So generalization of this is provided by the notion of solid bounded analytic ring. So analytic rings is understood in the sense of Clausen-Scholze. So that's datum of a condensed ring, which you can think of as just datum of a topological ring, plus, so let's say, so analytic ring R is the datum of a condensed ring, which I will denote by R underlined, plus a certain subcategory stable by all limits and co-limits of the derived category of underlying R modules, plus some other properties, which you can think of as a category of complete modules of this topological ring. All right, and then there are two more adjectives, which I mean, I think these notions were studied and analyzed in the work of Juan Esteban on the analytic Durand stack. So solid roughly means that the analytic ring structure very vague here, comes from some R plus. So let's say R is a Huber ring, for example. Then you only want to consider the analytic. So to any choice of open integrally closed subring R plus, like in the theory of adic spaces, you can attach a certain analytic structure on R. And you somehow only consider the ones which come from this construction. So that's really an analog maybe of just Huber pets. And the key notion maybe is a notion of bounded ring, which corresponds to the state condition here, which, well, basically say that you have a pseudo-uniformizer something. It's really an analog of the state condition. If an element of this ring, you can think to it as a function, so you can think to it as a morphism from polynomial algebra in T to your ring. And saying that it's bounded means that, okay, let me put it another way. It's basically, geometrically speaking, it's basically telling you that any function is bounded. So any function, you can think to it as a map from the analytic spectrum of this ring to affine algebraic affine line. And you want any such two factors for the analytic affine. Okay, and so that's our ambient category. And inside that, we have this category of Dagger perfected rings. So this is like a full subcategory inside. And what's the condition? So R, which is solid bounded analytic ring. Whenever you have such an R, you can define its Dagger radical, which is roughly the subset of elements divisible by all powers of a pseudo-uniformizer. And because of the condition of boundedness, I'm sure that this is an ideal. And so roughly you multiply a function which is overconvergent convergently close to 0 by a bounded one, it remains convergently close to 0. And because of this, you can define for any such R, its dagger reduction. Which is a condensed ring, which you endow with the induced analytic structure from R. All right, and now you say that R is dagger perfectly. If this dagger reduced quotient is a perfect ring. Meaning that it is an analytic ring coming from a perfectly affinoid type. Okay, so how do you do? Okay, I'm just finished by stating maybe the definition and then stop. So now the definition of the prismatization goes as follows. So, okay, for simplicity, I will maybe, because we mostly thought so far about the relative case, so fix C as usual. I'm only considering the relative version of the construction. And then let X be an adic space over C. Then you define the prismatization of X as, well, so we want it to be a stack on this category, I mean, on the opposite category of dagger perfectoid rings over Y0 infinity. So like R, the dagger ring over the analytification of this one. And then you do a definition by transmutation. Somehow I fix the base to avoid discussing what happens exactly in the absolute situation. And then I can simply define X prism of R to be X evaluated as before. So cofiber of the limit under Frobenius So what am I doing here? I'm basically just using point 1, this idea that what I should try to geometrize is uncompleted perfection of prismatic cohomology. I like to apply this to the affine line, but affine line I can write it as colimit under multiplication by P of the affinoid ball of radius 1, which has a nice formal model. For this nice formal model, I can take its prismatization in the sense of Bhatt-Lurie and then take the perfection of this. So that's basically what you input here. And of course, you have to really define this as an analytic ring so that this makes sense. So this is really cheating. But this is basic, I mean, and this is maybe only true up to some simplification. But what really allows you to analyze this object and understand it is basically I mean, this could make sense a priori for any solid bounded analytic ring, but the nice feature of these dagger perfectoid rings is that there are extensions of the perfectoid ring by something which is dagger nilpotent. And in the case where everything lives in characteristic 0, for the perfectoid ring, it's easy to control what happens when you play with bit vectors. It's basically Fontaine's A-inf construction which arises. But for the dagger nilpotent part as well, because it's like, it's actually because of everything is infinitely divisible by P, it's a QP module. And by ghost components, you can write bit vectors as a product and explicitly analyze what this cofiber does. So this.
Can you repeat what's inside of the X? That's cofiber of what?
It's a limit under Frobenius of.
Limit or colimit?
No, limit.
Okay.
It takes the Frobenius perfection of just multiplication by so xi is the generator of the ideal I, which it's a Fontaine's theta, and then you just take the multiplication by all these negative coordinates translates, and then invert p at the very end. Okay, but I should stop. Sorry.
Questions?
I was slightly confused about this weight vectors. This is W is weight vectors, right? What analytic structure you put on this?
Right. So first of all, yeah, I mean, as a Condon string, it's just given by. I did not define what R not is, right? But it's a set of R bounded elements in R. This is something you can define. So this is what you do. So it's like this will be represented by a certain co-limit of theta of the graphs. And then the analytic structure that you take is you have the Teichmüller lift, which goes from R to okay here, just here, but at the end I take an invert Teichmüller flat. It's from R, which is given by the Teichmüller lift, and then you take the limit under Frobenius, and you take just the analytic structure on this, which makes this element so. R plus.
So do you have any universal property of this?
Universal property?
Yeah, I mean W is that a right to draw into some whatever.
I don't know. I mean, we did not really investigate. I mean, yeah, that's right that you could study a notion of delta ring in this setup and try to see if vectors are adjoint. You forget. I don't know.
So if X is the profatoid, then what is this one? Like if you X is the profatoid, what are space?
X is perfectoid. Well, first of all, maybe it's something I can say is that okay, this is defined as a functor on dagger perfectoid spaces, but you can always like say restrict to perfectoid test objects, and then left can extend back. And what this is somewhat like taking the diamond in some sense of this analytic stack, and in this sense, like diamond of the prismatization of X is basically the diamond of X in the usual sense of this world, based on p-adic. This based on p-adic is explained by the fact that here the test category is really all perfectoid spaces without any restriction to characteristic. So this is something which is also denoted by maybe something like that. It's a relative version of this space Y0 infinity. But it's not isomorph, so that's maybe one more diamond on top. But this is still not. I mean, this one is it's the diamond of a certain analytic adic space over ZP. But it's not even in the perfectoid case. It's not isomorphic to the prismatization. So it's true that if X is perfectoid, X such state is just the same as it. I mean, right. But away from the Hodge state locus and all its Frobenius translate, you still see something different. So this will be like the Durham stack, the analytic Durham stack in the sense of Juan Esteban of the perfectoid space, which is not trivial.
Thank you.
If I want to define naively what dagger perfectly is,
Yes.
okay, I take one affiliate perfectoid, another affiliate perfectoid, and I shrink the bigger one. Right?
Yeah, okay, that's why I think this terminology is bad. And if you can change it.
So
It's
I'm
not-
not getting any nilpotence or anything like that, right? But any of the elements of that.
Right, that will already be reduced, I guess. Dagger reduced. Like something, like for example, also if you take just functions on the torus and you extract piece roots and take just the co-limit of this, that's also not dagger perfectly. So it's not like it's not a topological ring which has embeds in its completion, which would be perfectoid. It's rather the opposite. It subjects onto something perfectoid, and there is a certain the kernel is a dagger. So one example which is not perfectoid is, for example, you take this ring of functions, something like a co-limit of field of data algebra. But that's an example where it's already just the dagger reduced quotient is theta. It's functions on the overconvergent disk of reduced theta.
Arthur?
How much bigger does one expect the whole category of perfect complexes on the V side to be in the image of alpha star?
Right. So as I said, so you can make sense of diamond of this also as an analytic stack, and this gives you a natural map from pullback map from perfect complexes on this prismatization to perfect complexes on this adic space. I mean the diamond, which again makes sense by descent. And we expect this map to be actually on equivalence. So if you specialize to perfect complex which are supported on the Hodge state log, sorry, I should say, or smooth, which is better.
Smooth over what?
As before, like either a p-adic field or C. So let's say, for example, over C. But also over QP. But if you specialize to perfect complexes which are supported on the Hodge state locus, that would tell you that perfect complexes on the V side, that's what I wanted to come to at the end, are actually the same as perfect complex on this Hodge state stack. So you really get everything this way. You can also restrict to vector bundles and add Frobenius equivalence structures on both sides. And you know that what you get on the right-hand side, by results of KLILU, is a category of ZP local systems on Higgs. So that gives you a description of ZP local systems in terms of something more analytic.
Thank you.
But the R gamma prism X that you would get, does it compare to the Biedermann plus cohomology?
The Biedermann plus
cohomology, I don't know, does it compare this quasi-co over the relative curve, over the curve, does it compare to known cohomology, to Yodokato?
Well, you see, in particular, in this case, by looking at on the morphism of the unit object, you see that at least in the smooth rigid case, what that should be cohomology of the structure sheaf here should be cohomology of the structure sheaf over there, which is basically Poetal, the base change of Poetal cohomology. I don't really know, even if I try to motivate the construction of the stack by considering some kind of Frobenius perfection of prismatic cohomology of a formal model, I don't really know what the cohomology of the structure sheaf on this stack computes in general. But at least in the smooth rigid case, basically QP Poetal cohomology with some base change. ZP.
Okay, thank you very much.